Hello, everyone. My name is Michael Starbuck, and this is my project for the first data science practicum at Regis University. For this project, I did a project on predicting credit default risk with machine learning, and I used R for this project. A little bit of background on the project. Whenever anybody is lending anything to somebody else, there's always the risk that they will not get that thing back. Maybe a library is lending a book to an individual. There's always the risk that that book is not coming back to the library. Even for a car rental company, there's a risk that the car may not be coming back, or that the car will come back wrecked and not worth as much as it did when it was lent out. So financial institutions are no different. When they lend out money to consumers for houses, they lend out mortgages that are worth hundreds of thousands, even millions of dollars. And so it's very important for these financial institutions to know before they lend that money if they're going to get that money back. Right now, they have underwriting processes where underwriters look at stacks of paperwork, and they look at all kinds of data, and it's a very manual process where they look at all this and they decide whether they're going to lend that money to the individual or not. So it would be more efficient for the financial institution to have an automated way to do this, or at least a way to assist the underwriter in that process to help reduce their overall risk. So the data that I used for this project was found on Kaggle.com. This was a competition that was started with Home Credit Group, which is a lending company that does mortgages, and they put this competition up on Kaggle's site to try to get a machine learning model that will help them predict default risk for individuals. There is a lot of data on the site at the URL I have on the presentation here. There are many different tables with lots of different data that has the relationships, and for this project, I decided to focus on the main data table. Um, I decided not to add in all of the other data that's available because this main data set is very large. There are 122 columns in the data set, including the class variable, which is called target. And upon exploration of this data set, I found that there are over 9 million missing values. That is over 24% of all the data that is missing. So there's definitely going to be a lot of work in trying to figure out what to do with those missing values. There are 52 categorical variables in this data set that I converted to factors before starting the work. And then after I converted the factors, I started to explore the NA values. So you can see on the top right here, the first thing I did was create a column that counted the NAs by row. And I just wanted to see if there were any rows or multiple rows that I could eliminate that had maybe more than half of the values were null and missing. What I saw here in this histogram is there's really nothing past 58 or so NAs. So there were no rows that I could eliminate. Definitely the spike around 50 was interesting to me. That means there's 50 columns there that there are a lot of rows that just don't have that data. So my next step was to create a matrix that showed the NA count and the percentage of rows by column. So I have a sample here in the bottom right of the top 10 values in that table. What I found was there were 44 variables that had over 50% missing values. So instead of just going right into it and dumping those 44 variables, I wanted to explore them a little bit more. So there's definitely more work to do with the NA values. But before I did that, there was one more column that I found in the summary that looked a little off. The days employed variable was a variable that had negative values. So it was the number of days before today that the consumer started working. So there was always a negative value. But the maximum value for this field was positive. So it made me want to explore it a little bit more. So I created the box plot that you see here on the right, just to try to figure out what the distribution was. Why am I seeing positive values? So what I found was that there's this one positive value way up over everything else, and everything else is negative. So what I found upon further exploration is there were a number of rows with this value, and it seems to be some kind of default value. There are no NAs in this column, so this must be some kind of default value. So what I did was I went ahead and turned all of those into NA. So now I have one more column with NA values, and so go ahead and start exploring the NA values next. And before I'm just eliminating NA values, I decided to look at correlations to see if there are variables that are highly correlated with a lot of missing values that I really should not eliminate. So I went ahead and one-hot encoded a lot of the categorical variables and created this correlation matrix and plotted it out on the left. Um, as you can see, there are so many columns that this is just not useful even a little bit. I see a lot of red. Red is the high correlation. I see a lot of that in the bottom right, but with the one-hot encoded values, I expected a high correlation between those values. So there's really nothing I can do with this plot here. So I went ahead and created a vector that showed the correlation with the target variable and compared that with the NA table. So what I ended up doing was the variables with over 60% NA that were not found in the top 30 most correlated values were eliminated. It turned out that that was all of those values, all of those variables were eliminated. I also found two variables, organization type and the hour APPR process start, that were just very low correlation. And so I went ahead and eliminated those as well, just to get rid of some columns that I don't need. I went ahead and tried to impute the remaining missing values, and it just kept crashing, just wasn't going to work with the amount of memory I had, just because we still have so many missing values. It just didn't work. So I went ahead and moved that NA threshold to 40% and eliminated a lot more variables there. I found that there were a couple variables that had 40% or more missing values that had high correlation, so I didn't eliminate those. I kept those, but went ahead and moved on from there. So after eliminating all of those, I was left with 65 variables, including the target. And now, now that I have a more reasonable data set, I tried to impute again, and once again it failed. I still did not have, I still had too much data to impute. So what I did with the factors was, instead of imputing the factors and trying to find new values for it, I just created a new level in all of them for none, and just accepting that we're going to have some missing data. It's in real life, we're always going to be missing some data, and so none is just going to be a new level for the factors. And from there, I was finally able to impute. I used the mice package. Was not able to do multiple imputation, once again because of the memory issue, but I did 3 iterations over the one imputation. Was able to come up with some imputed values, and using the classification regression tree method. And from there, I was able to finally go on and start building some models. So what I decided to do with the models was I tried 3 different types of classification models. The first one was random forest, then a naive Bayes, and then the K nearest neighbors, or KNN. And looking at each model, I decided the balanced accuracy is going to be the best to evaluate the performance on this particular data set, because there are a lot more values that are the class 0 as opposed to the class 1. The class 1 is a default and 0 is not. So there's a lot more zeros than ones. It's really not a balanced data set. So the balanced accuracy is going to be better than the pure accuracy. And for the training test split of the data, I went with a 70-30 split. So once I had the data split, I built the models. The random forest was the first one I built, and I found that very few records were classified as a 1 in the test. There were out of 300,000 rows, there were only about 30 or 40 that were classified as a 1. So we ended up with a good accuracy level because of the unbalanced data set, but the balanced accuracy was at 50%, which is really not better than a pure guess. So we could just be guessing 0 or 1, and we could be guessing 0 all the time and end up with better than that. So the next thought of mine was, instead of using 100 trees, maybe I increase the trees. I plotted this out and found that the error is leveling off, so increasing the number of trees is really not going to help me. So the next model was the naive Bayes, and the result of this was more records were classified as a default, or had the 1 value for the target variable. But the pure accuracy was lower than the random forest. You can see here it's about 88% versus the 92% for the random forest. But the balanced accuracy was a little bit higher because there are more 1 values predicted. But still, a 55% balanced accuracy is still not much better than a random guess. So we're still not quite to where we want to be with the models. So the third model I tried was the KNN, and this was the best accuracy, pure accuracy result yet, 94%. And it was also the best balanced accuracy, which is a surprising huge jump to 71%. Which is very much improved over a random guess. So go ahead and select this model to optimize it, and see if we can even improve upon the 71%. So the next step was trying to find the best value for K. In my original model, I used K equals 1. So I created a for loop to track the balanced accuracy at each value of K. As you can see in the plot on the right, the accuracy went down with every value of K. So the optimal value was the one I started with at K equals 1. So that will be the model that will be selected with a surprisingly high 71% accuracy rate. So after selecting the model, just coming to a conclusion that it really is possible that that financial institutions can use this or a model to assist in the underwriting process. And back to the beginning when we talked about the data, there's a lot more data that's available. So it's possible that adding in more data from additional tables, it's possible that the accuracy can be improved even more, and it could be even more reliable. It's also possible that getting together with the bankers and telling them to collect more data and getting rid of all these missing values, it's possible that it could increase even more that way. So like I said, it's a higher percentage accuracy than I was expecting. So it was a successful project for me in that case. Uh, so that brings me to the references. Most of the code that I used and um, work in R that I used, I got from class materials from MSDS 680 and 660 here at Regis, and I got the data from Kaggle as shown here. So thank you very much.